So it's time to say welcome to Professor Imad Al Qadi for his keynote lecture. Everybody of us know Imad Al Qadi is really top-level researcher at Illinois. He's director of the Illinois Transportation Center. He's really well-known worldwide. So I'm very proud to say hello and welcome to Imad, who came from US just for this lecture. So double thank to Imad, because tomorrow he will fly back home because he has lectures in his courses, but he was very happy to join us just for this lecture. Imad, say thank you is not enough. It's not enough for you, but we are really, hungry to hear this important lecture about connected and automated vehicles. Please, Imad.
I'm completely honored to be here, and thank you so much. It takes an army sometimes to put a conference, and Professor Crispino, I guess you did an amazing job with your leadership, so thank you so much for inviting me too. So let's see if I can get my presentation up. Is it up? Oh, all right. Again, my name is Imad Al Qadi. I'm with the University of Illinois, and I don't know if I can see the presentation on this one here. Excellent. Thank you so much. So when you asked me to talk about this topic, I thought this group is a pavement group, and definitely I wanted to focus on talking about pavements and what are the challenges that we have as we are moving forward into the era of connected and autonomous vehicle. So in order to make sure that we are all on the same page, I would like to talk first about the factors that impacting the mobility of goods and people. First, we are all concerned about safety. In the United States, during, for example, the COVID-19, the number of the miles traveled reduced from 3.3 trillion to 2.8 trillion. But at the same time, we saw an increase of 18% in the fatality. So that was a big concern for us. In addition, congestion is a big problem for us because it is costing us money. It is also impacting the repair of our roads, and it's taking a lot of time from the workforce that we have. And third is the climate change. Transportation is responsible for 30% of the emission or greenhouse gases, and now it is the #1 sector that is responsible for the emission that we have. Most importantly is that the emission that it's coming from the transportation, it's mostly coming from the fuel and from oil, and that's by itself, it's a concern. Now, all this gonna be contributing to the economy and the society. Our role here is to talk about the pavements part and the resilient part of the pavement. So as we are moving forward with this, the three things that I mentioned, I wanted to see how's the connected and autonomous vehicle will impacting that. So as we are moving into connected and autonomous vehicle, the speed of the traffic will increase by 8 to 13%, which means here that we will have a better flow, we will have less use of gas, and will keep increasing as the penetration of the autonomous and connected vehicle is increased. Ultimately, we will have an optimized traffic flow and definitely reduce the congestion that we have, because you will have a better connection between the vehicle and the surrounding, or call it the infrastructure. As to the safety, we will have a much better reliable time as we're moving forward. So as we start applying this technology, the conflict that we have will be reduced by 47%. Whenever we have 25% of the market is autonomous and connected vehicle. As this penetration is increasing now, the conflict will be reduced and the safety will be advanced even higher and higher. Then we got to the climate change, and the greenhouse gas is definitely going to be decreased as we are getting more into the eco-driving and the platooning, which I'll be discussing here in a minute. And also the emission will be decreased as we will have a better handle of the traffic signaling, and of course the electrification, which also I will be talking about it a little more. So ultimately that will get us to what we are hoping for is the net zero emission through especially the electrified mobility. Now, with this here, we need to look at the market. What is the market going to look like in the near future? So I tried to look at like maybe less than a decade from now and look at different things. For example, the global KVT will grow exponentially. For example, the value in 2020 was at 76 billion. It's in 2030, it's estimated at 2.2 trillion. If we look at the communications between vehicle and X, which means the surrounding, the infrastructure, and so on, the value of this market in 2021 is at 630 million, and it will grow by 2029 to 11 million. As to the renewable energy, the industrial revenue right now is at 860 billion, and in 2029 is expected to reach 1.6 billion, and that's coming from many different areas, solar, wind, and so on. Then we get to the electric trucks. And by the way, the trucks in the United States is suffering big time because we have a very big shortage of the drivers. Right now, we have like 60,000 shortage in drivers. And of course, we have some laws of how many hours they can drive and so on. And please remember that almost 75% of all the goods in the United States, they are traveling on trucks. So the electric trucks in 2020 was around 392 million. In 2030, that's going to be increased at an annual rate of 26% to reach almost 3.86 million. What does that mean altogether, these numbers here? It means that we need to harness maximum capabilities of the autonomous and connected vehicle and trucks, which require to have some kind of collaborations between all the stakeholders in order to have a better future for the better use of this. So this emerging technology will take us to the next generation of the pavement challenges and opportunities. And I promise you that I will not be using any equations in my presentations, nor I will be using plots. So I'm going to be just focusing on scratching the surface and try to push the envelope a little bit of what we really need to do as we're moving forward. Pavements, especially the Romans, they built it for more than 2,000 years, and we have some of these pavements still there. Right now, we designed the pavement for 20, 25 years, and after 10 years, it's failing, which means that we're doing something maybe not right. And we need to fix this as we're moving forward. And then I believe, at least I think, that the rapidity of the technology in the transportation, I don't think that we ever have seen something like this. It's moving very fast, and this change in mobility, it's becoming the norm. If we're talking about the drones, the first and last miles, we're talking about electric trucks, if we're talking even about the flying taxis, all this is coming with the electrification, the connectivity, as well as the autonomy. I'm going to give here two examples. Like if we are moving goods, in the future, these goods are going to go through the trucks, which we're going to be seeing autonomous and connected trucks, platoons using our pavements, and we need to address that. And this technology is moving really fast, but now we're having some hold for a reason or another, which I will be touching on that. But also, as we are getting this to a specific facilities, that's where we're going to be using the drones in order to take these goods to the houses, to whatever. Now, this will change the mechanism of how these vehicles is impacting our pavements. Now, they're going to be more used on the highways, and they're going to be less used inner the city. But also, some of my colleagues now, they are working on the congestions in the sky, because we're going to be seeing a lot of these drones in the sky too, but that's a little of my field. So this requires some kind of a seamless integration across all these platforms. From the vehicles, it's the autonomy and the connectivity and the electrification, and most definitely we're going to be using more of the shared riding. And from sensing or the health monitoring, we're talking about wireless, self-powered, which means that the instruments that we're putting in, it's going to be serving for a long time, mostly now. They're like 2-3 years and they're dead. And it's a network-wide communication, and it's got to be secure. The cybersecurity is a big, big issue as we're moving more into the autonomy. I mean, imagine if you're driving a car, autonomous car, and somebody is taking over driving your car from you, and is something that people are looking at it, and it's a serious problem. From the pavement's point of view, we need to start thinking, what is the true meaning of the self-healing, and how we're going to be doing a continuous part sensing and real-time assessment and energy harvesting too. So from the pavement systems, I'm going to be looking into three things today. I will be looking into the materials, and of course, we have the loading that it's applied to this material, and then the resiliency of the pavement itself. So I'll take these one at a time. The first, for engineering the pavement materials, we need it to be adaptive, self-healing, long-lasting, and sustainable. Now, if we look at the quarry, and I'm going to be focusing more on the asphalt, by the way, because that's my area of expertise, I would say, so I apologize for the concrete people. So if we look at the quarries, there's a lot of autonomy now happening in the quarry. But something is really also important that it's taking place is we can use the drones now, and it's going to go around this pile of aggregate, and it's not just telling you the volume, because knowing the volume, it's very, very easy. Now, we can even get the shape of the aggregate and put these shapes together with a neural network, and we can use this now to come up with the volumetric design for the asphalt concrete. This is where we should be going in the future. And as we are putting this, like for example, in every maybe ton of aggregate, we can put like 1% of that smart aggregate, which is going to tell me it has sensors in the aggregate, which use the shape of the aggregate, and that will tell me what's the stresses that it's happening in the pavement itself. As to the asphalt, we have been doing a lot of advancements in the asphalt binder itself, but the truth is we're still looking at this as a viscoelastic in the linear area, which is a very, very small. But if you look at this simulation here, if there is any compression, it's all happened in the asphalt. So we're not talking about 100 micron, we're talking about 3,000 micron, which means that the material is completely nonlinear. And what the testing that we're doing right now, we need to expand it to the nonlinearity if we need to understand what's going on. And of course, we can at that time apply the principle of temperature and loading for our analysis. For the aggregate, if we're talking about low volume roads, we should be considered as a stress dependent. Then we definitely wanted everything we think about now, we need to think about recycling. We need to make sure that maybe 100% recycling. So we're going to be using some materials like plastics, which is, I can assure you that it's more than 80% of the plastics are going to the landfills. But at the same time, the plastics are many different types. We cannot just keep doing what we used to do before, is trial and error, or take this plastic and put it with the asphalt and see if it's going to separate or not. This is not the way to do it. What we need to do now is to make sure that we look at three things. First, is this going to be reliably applied as a recycled materials, and it's going to be really beneficial from the life cycle assessment? The first question. Second, I need to be looking into the rheology of this material, but the rheology may be after I extract it, which means here I'm going to be first mixing it, maybe with the aggregate, and then try to see how these materials behave. And then now we need to add another thing, which is the chemistry of the material, which we usually don't include. And I think this is a very, very important part as we're moving forward. And then we can look into the performance testing, which I will also touch on a little bit. Like, if I'm going to consider just two things, which is the cracking in the pavement and the rutting in the pavement, I want these materials not to rut and not to crack. We need to come up with some performance testing, and I'm sorry for the second video, it seems that it went wide anyway. But anyway, this is a Hamburg test. But here's something like, if I wanted to do a cracking test, I cannot do, for example, an indirect tensile I'll get from that cracking. because fundamentally that's wrong. What I need to do is understand the theory and understand the fundamentals. That will work if we are talking just about low temperature, but if we're talking about surface temperature, you must have a crack if you run a test. And I guess as an academic, sometimes I'm surprised how sometimes we just overlook some of the basic science or basic knowledge when we are developing testing. Running test, it's working as practical and empirical test. But as we are moving in the future, we're going to have different materials. We need to make sure that we have a test that we will be able to predict how the material is going to behave. Even with the balance, which is, I'm very, very pleased actually, that we have a balanced mix design, which based on cracking and rutting, there is an important factor missing, which has to do with how stiff the material is. This is another one that we do have these values that should be added because that's going to be dictate if the mix is balanced or not. As we're moving forward, we need to fix these cracks as it happens. There is two ways to do this. One is maybe you can have capsules in the materials, and as the stress is increased on these capsules, it will open up and it will release some kind of a polymer that will allow to fill the crack. The other approach, which is developed by some of my colleagues at the Beckman Institute at the University of Illinois, is to look at this like the human body. It's the microvascular system. And this one, whenever there is a crack, you will find that it will repair it, then it will repair it again and again and again. And these are the new technologies that we should be start applying into our pavement. There's many rehabilitation techniques, such as the electromagnetic induction, which required to put some steel fibers and use this in order to heal the concrete. Here's another thing that we are working with the Army and the Army Corps of Engineers, and the Fermat Lab, is to look at the electron beam accelerometer. Now, this came from the fundamental understanding that the aging of the asphalt, it's happened just in the upper half centimeters. If we try to repair this upper half centimeters, we definitely can rehabilitate the pavement or give it a very nice lift, surface lift, if I may say. So this is ultimately how it's going to look like. This is the conceptual plan for the projects that we have. And of course, we have the cool pavements. There's a lot of work going comparing concrete to asphalt. That's not what we need to do. What we need to do is to try to have a pavement that it will be having high reflectors, like asphalt is by way much lower albedo than concrete. So the concrete is better. But if you leave the asphalt for a year in the field, that albedo will go up to maybe 0.15 to 0.2. The concrete is 0.25, so they're going to be similar at the end. So think about it that way. But what we need to do is, instead of comparing this, try to see what can we add materials to increase this kind of reflectivity and increase the albedo. Moving into the pavement loading, and I want you to keep me on time. All right. So we need to minimize the damage and use energy harvesting or utilization. So let me start by saying the load that we apply to pavement is coming from different tires. It could be wide, it could be two. So these kind of, for the roads, that's very maybe simple. If we get into the airplane, that's become very, very complex. And actually, I remember being in Milano in maybe 8 years ago, when the Air Force, they were trying to think at that time, getting the F-35. And the main concern actually is not the load that is coming from an airplane like this. It's more coming from the tire pressure. Because when the tire pressure for an airplane like the ones I'm showing, maybe it's 250 PSI. But if you go to a fighter like the F-15 or F-16, that's 350 PSI. That's going to do a lot of damage to the surface of the pavement. But most importantly, that these damage, they are not coming just in a load going in this direction. They go in this direction, this direction, this direction. And when they break, that load will be increased dramatically. So anytime we're trying to model the load, it has to be in 3 dimensions. We used to send this to South Africa, actually, to measure the stresses in 3 dimensions by applying different loads and different tire pressure and so on, until we came up with developing a model ourselves that we will be able to get the stresses in 3 dimensions so we can use it in our finite element modeling. But to make this faster now, with knowing the properties and running so many of these finite elements, which takes some time, using now the data sciences and using the deep learning, we will be able now to predict the contact stresses in 3 dimensions for any tire. And that's what I would consider a step forward. So for example, if you look at an airport where the pressure or the highest shear stress is going to be 3 to 4 inches below the surface, you need to have an advanced modeling in order to predict when this happens, where this is going to happen, and under what load. And that's where the finite elements become very important. And that's the only way I'm going to emphasize that you will be able to predict slippage like this. Now, also, we always consider the different kind of failure criteria, if it's fatigue or rutting, as they are separate. Actually, in real life, they are not separate. You have fatigue, you have rutting, they are all happening together, and that's where we have a new model, which we call it the domain analysis, that will allow you to consider the shear and the normal stresses all together and divide the pavement in order to see where the damage is going to be. As you can see here, I can tell, but just at the picture here, where the maximum stresses are, and you can see it's like almost 2 inches below the surface. This is my favorite slide, by the way, because this is a new thing that we're looking at, and that's going to save us a lot of computational time and money. This is using the graph neural network, and this is borrowed from some people who were doing fluid mechanics. I'm going to look at the department head who's working on fluid mechanics. This is something that it's really neat. These people now, they are modeling the fluid, and you can look at the 2 pictures, and you can see what they are predicting is similar to what's the ground truth is. What we are doing right now, instead of 3 days to run a finite element model, complex finite element model, and by the way, University of Illinois has the fastest computer in the world, supposedly, and it still takes a long time to do it. What we are doing now, we look at each element, which there are, sometimes hundreds of thousands, in the model, and we predict each one of them, so we will be able now to predict what's the finite element could have given me in few minutes rather than spending 3 days. So this is something that we're working on right now, and hopefully that will save us a lot of time and will allow us to apply these kind of technologies in the future to have a better prediction of the pavement performance. A lot of people, they talk about the platoons. So if we look at the platoons, this is to have trucks driving behind each other with a specific distance. In the United States, depends on the states, usually we have between 200 feet to 250 feet between the trucks. Now people are saying they're gonna have 10 feet between the, I don't think that I will ever see this in my life, but I think we will see 50, 60 feet between them. Now, as these trucks are gonna be moving like this, and they could be as low as 2, and they could be as high as, 10. Right now, the experimental work is 1 to 2. You're going to see more damage happen in the pavement. I'll give an example. Where I live in the state of Illinois, we found that in the interstate system that we have, 87% of the roads are platoonable, which means that they can platoon. That's during the peak hour. If it's off-peak hour, it's 93% of the network is platoonable, which means that if we like it or not, they're going to platoon. Actually, when you are driving, sometimes you see the truckers drive behind each other because that can save up to 15% in the fuel. So this is really important. But at the same time, as you look at this schematic here, as the vehicles just keep adding in the same spot, you're going to be having channelized. This is going to do a lot of damage to the pavement. What we wanted to do is to change this challenge to an opportunity. And simply, if we take this load and we just keep shifting it, as we are shifting the load now, we're distributing the load over a bigger area. And as we put it in a bigger area, at the beginning, we thought that we're going to be shifting each truck, which is going to be a little tougher from application point of view or implementation. What we decided to do is to get each platoon and shift a whole platoon. So if I look at this here, there is three things that is important. First is the rest period, which is how far I want these platoons from each other, how much I need laterally to be able to have them from each other, and what is the number of trucks on the platoons. I can tell you in a study that we published recently, we found that we can, with the platoons even, increase the service life of the pavement if we design it well, and it's going to be much, much better than what you have from human-driven trucks. So this has been published recently. Now, let's look at the electric trucks as part of the loading. Trucks can cover up to 100,000 miles in a year. And I wanted to just put some numbers here to compare to. One is the Tesla Cybertruck, and compare the initial cost, the charging cost, the operation cost, and the range of driving. Please have a look, I don't want to read the numbers, between this and what we have from a diesel truck. What you can see from both here, that the Tesla or the electric truck is much better, but there is a little problem here. This problem here that I need 30 to 90-minute charge to reach 80%. And usually you have a trucker drive maybe 600 miles, and I don't want to stop for an hour and a half in order to charge. That's called inconvenient. So this is one of the problems here, is the charging. Now, although the electric trucks may be expensive from the emission point of view at the beginning, but over the lifetime, you will find that the greenhouse gases will be lowered by 40%. There is another major problem here, other than to stop for the charge, is to look at the weight of the trucks. I said I will not show any plots, but that's not my plot, so it's okay. So that plot here is showing that electrical cars are in increase. The red one is for the trucks. We're just about to increase the number of electrical trucks, okay? Now, here's our concern as a pavement. If you look at this schematic here, this is the engine, and this is the gas tank. And you can find the engine is around 3 kips, the gas tank is around 1.6. And if I'm going to be changing this with a battery, depends what kind of batteries I have, I'm increasing the weight based on what's written in the literature is by 2 kips. But the truth is, I'm increasing this almost by 12 kips. So that's going to be a significant thing that we need to worry about. So frankly, if you look at the whole thing, as reported, is 2 kips, and in the United States now we do allow an increase for trucks which use renewable energy, which is including electricity, to go up by 2 kips. But the truth is, and I'm talking to many of the trucking industry, that's going to be an increase of 8 to 9, because you have like 12 to 13 kip, the weight of the electrical batteries and so on. If you take the gas and engine, the difference between around 8 to 9. So that's going to be a very significant, unless some advancements going to be happening, and that's going to be like 4 to 5 years from now. So what we need to look at is that there's going to be an increase in weight. What is the penetrations going to be of these electric trucks in the field? What is the charging intervals, and how often, and where is these stations? That's also going to play a role. And most importantly for the pavements people is how much this increase in the axle is going to be impacting the pavement. And the final topic is looking into the pavement resiliency, which is talking about the safety and how to predict the pavement performance and the economics of it, as well as the preservation. When we build the pavement, one of the most important things we looked at when we pay the contractor or try to predict the performance is look at the density of the pavement. We all use nuclear gauge, and I think I can say that safely. We all know that it's not very accurate, and it's just based on how we calibrate it, but we go with it. One way to do this is to have the ground penetrating radar use, and I'm going to emphasize here, in the right way, based on the fundamentals and the theory, and not based on regression. Because based on regression means that you want it to calibrate it all the time, and that depends on the project that you have, and that might not give you a good results. So this one here, first, you need to make sure that you are cleaning the signal, make sure that the signal is not impacting by the vibration, and that's a very, very sophisticated work that has been done recently. Oops, can't lower it. Here we go. So this is now part of a project that's sponsored by the Federal Highway Administration. We were able now to put this on a vibrating compactor, and we canceled everything from the vibration that you have, from the noises that you have, the electromagnetic waves that you receive is completely clean and clear, and you will be able to know what kind of density you have, and this density will go back into your pavement system, and you will be able to evaluate your pavement system in a very, very appropriate way. And recently now, we are playing with this. We just started, is to have the radar, instead of putting it on the compactor, we are having this now on a drone, and we are doing some testing on this, so that also all the data that we are getting, by the way, it's in what I will call it near real time, we collected in a wireless way. Yesterday we heard Richard and Gerardo talked about the safety, and most importantly, it's coming like from driver vehicle environment. We can be in control of the pavement part or the friction that is impacted by the vehicle and the environment. And we mainly used the luck wheel skid trailer. And I apologize if I can offend anyone, but this is very expensive, it's time consuming, the results are variable, and we are taking it every X number of feet. So frankly, we don't have really good data with this approach. We need to do something a little different. This is a project that started looking at the friction prediction via the machine learning, and also looking at this from the computer vision techniques. The way that this will work, I'll show it in the next slide. We're going to be needing a lot of database preparation. We need to look into the computer vision algorithm, and this is going to be a very complex equations that we started on. And then use the machine learning model development based on results that we do, and then we have an automated system. So if I'm going to put this here, it's like this. You're going to be collecting data, and now we're looking at data collected in 360 degrees. This data will be reconstructed, the surface, to a very, very small level. And then after that, we'll try to predict the surface frictions from the texture. Actually, the friction is coming from the texture. So what we're trying to do now is to collect as much as we can data, and we do the analysis, and that's where we're going to be able to get the friction without using the luck wheel. Then we have two ways in order to control the vehicles, the autonomous and connected vehicle when they are driving. One way, which some of you who have an autonomous and connected vehicle, the vehicle that you have will look at the paint on both sides of the pavement, and that's where, I guess, it controls the vehicle direction. Now, if it's rainy, if it's snow, this system will fail. Even sometimes the satellite system will fail. So we need to have something that is completely reliable at any time, and that's where the pavements people can help in. So one of my colleagues is working on this system, which you're gonna have electromagnetic signature. This is completely independent of the weather, and that will be able to direct the traffic. We did successfully the experimental work on this, and this is really gonna be help. Most important thing is we need to consider that when we put this in the pavement system, how we're going to be rehabilitating the pavement, and how this is going to be impacting the pavement, and how deep we need to do it. So this is part of the development of this technique. And of course, we cannot talk about pavement without talking about sustainability. I mentioned that earlier, but also it's always we are talking about the environment, economy, and social. And there is this 3 stages, which is the material acquisition and construction, maintenance, use, and end of life. Of course, the use part or the use stage is the most, I guess, complex, but at the same time is the most important one. So this one is responsible for maybe as low as 45 or 50 to as high as 85%. And usually we are looking into 3 things coming from the pavements other than the albedo and so on that I mentioned earlier. The rolling resistance is coming from the structure, the pavement tire interaction is coming from the texture, the deformation, and the rolling resistance. We spend a lot of time on things that it doesn't maybe make sense. Like, for example, is the concrete better than asphalt when it comes to the rolling resistance? My answer simply is not, because most of the deflection is happening in the tire. 90% of the deflection is happening in the tire. There is much less deflections to worry about in this material. There is a little different, but it's not something to worry about. So the rolling resistance, it can cause as much as 30% of the fuel of a truck. And we definitely need to improve that. Here's how we can do it in a double way. First, yesterday we did hear about using for the International Roughness Index, the golden car or the quarter car. Actually, we need to think, is this the right way to do it? So we need to go step by step. We went to half a car, then we went to a car. But I'm more concerned about the damage of the pavement. The damage of the pavement is coming from the trucks. It's not coming from the cars. So if I'm going to be concerned about the trucks, I need to model the 18-wheeler, the big truck. And that's what we did. So now we model for the roughness the whole 18-wheeler. And also we can predict the profile of the pavement with time. And that will be also impacting the dynamic loading on the pavement and can allow us to predict the damage. Please notice here that the roughness of the steering axle is different than the tandem. It's different from the rear one. And that's something that we do not even consider when we are doing the golden car. These now, the profiles, the dynamic loading can go into the analysis, and the dynamic loading itself will allow us to know how much energy harvesting we can get into the pavements so we can give it back. Of course, I will not spend time here. I think I should end the solar, thermal, hybrid. These are all systems also that will improve our pavement. Electrification also is something I want just to have 2 minutes if the chairman will allow me. Okay, I want to show this video, that's all. Okay, this is a video, and if you please don't turn the music. Okay, let's see if you can get it. We don't need, let's try to, okay, you need to push again. Let's see, here we go. This is a 2.9 miles. It's going to be over 1,000 acres that we are already finished the conceptual design in Illinois. And this is supposed to be a net zero emission. And this will be focused on testing the freights. You can see here we're doing everything from dynamic test pad to multi-model area, suburban area, agriculture, and energy harvesting. So here it will allow us in Illinois to do all weather conditions. You can see the testing of platooning. This is the urban area where we have the smart intersection. These vehicles, they're going to be negotiating who's going to be going first as they are moving. Agriculture automation is a big thing. The same here for transit testing. Of course, we don't want to ignore the wetland. And you can see here the roundabout. They all negotiate without signaling or stopping beforehand. The same is we're going to be working on the multimodal area. This place, by the way, it's in Chanute Air Force Base, and it's close to rail, airport, and interstate, all within 1 mile. It's going to be in all-weather testing, from snow to rain to fog. And we will be having, as I said, energy harvesting, as well as instruments to measure the pavement. So this is something will be coming soon. This is interesting project we're working on. And finally, currently we do pavement design on load carrying capacity, serviceability, sustainability. What we need to do is service dynamic demands of connected and autonomous vehicle, incorporate energy harvesting from solar to wind to mechanical, strategically locate charging and on-the-go charging facilities for the pavement, and design with self-healing materials and self-powered sensing, and of course account for the active lighting and vehicle 2X, everything around for the communication nodes. And one last thing I wanted to tell you, we are working right now on how we're going to be using quantum for the computation as well as for the communication, because they definitely much safer when it comes to the cybersecurity and much faster. So we already start working on using quantum for this. So with that, Mr. Chairman, thank you so much, and I'm sorry for... Sorry about that.